Hello and welcome to Lesson 9 of the GPS course. This is the first part of our discussion on GPS modernization and GNSS. We'll be talking about some new signals that are coming in GPS and some of the constellations that will be augmenting GPS in the future. GLONASS is available now and others are coming. Notably Galileo, the Chinese BeiDou system, the Japanese QZSS system, and there will undoubtedly be others. The configuration of the GPS space segment, 24 satellites for 24-hour worldwide coverage, is fairly well known. We've discussed that a little bit in the past. There are actually more than 24 available at any given time. This is so that there would be a few spare satellites on hand in case some of them need to be moved or retired. The fact that GPS has become more and more critical to all kinds of navigation over the years is a testament to the need to have these spares and to have this constellation be stable and constantly available. There are, of course, 6 orbital planes that are inclined 55 degrees and the nominal altitude in the neighborhood of 20,000 kilometers above the Earth. The oldest satellites that are in the current constellation, since Block 1 satellites are no longer being used. The oldest satellites were launched in 1989, and I say here, imagine using a personal computer of that vintage today. That, of course, it's a long time when one considers we're approaching 20 years that some of these satellites have been operating. So, it's not very surprising, given the system's age and criticality, that GPS needs to be modernized. And that modernization is, to some degree, already accomplished, and more is coming. And we'll be discussing some of the elements of that modernization. As I mentioned, the Block 1 satellites are no longer functional. They were retired. The last was retired in 1995. The oldest of the satellites that are operating today are the Block 2s. And it's amazing that their life has extended so far beyond the expected mean mission duration of about 11 years. They're radiation hardened. They were originally built to provide selective availability and anti-spoofing capability. Of course, selective availability has been turned off. This is the dithering of the clocks that was done to degrade the CA code positioning. Anti-spoofing is still available and turned on from time to time. This is the encryption of the P code into the Y code. The objective of anti-spoofing, of course, is to prevent bad guys from broadcasting signals that masquerade as GPS signals to confuse receivers, GPS receivers. In other words, the Block 2 satellites were built to accommodate these components, SA and AS. There are the upgraded Block 2As. The first of those was launched in 1990. The Block 2A can function continuously for 6 months without intervention by the control segment. That's, I suppose, good, but even if that were done, the navigation message, of course, would degrade dramatically in that amount of time. Block 2s, like Block 1s, have the rubidium and cesium clocks, or frequency standards, or oscillators. And while the Block 2s have extended beyond what they were expected to be able to do, They, of course, do wear out, and more of them will be retired as time goes on. After the Block 2s, we can look forward to seeing the Block 2Rs. R standing for replenishment. These have been launched. Some of these have been launched. The first in 1997. Block 2Rs really have some substantial changes from the Block 2. They can determine their own position using intersatellite crosslink ranging. They have reprogrammable processors on board so that they can do their own fixes in flight. They can change their own flight software on orbit. And the Block 2Rs can be moved to new orbits with a 60-day advance notice. They are a bit more autonomous than the original Block 2s. They have an improved antenna panel, which is useful in increasing the signal power of GPS, an always welcome component. And eventually there will be a constellation that will include primarily Block 2Rs, and this would be a good thing. The Block 2s and the Block 2Rs still broadcast fundamentally the same GPS signal, the CA code carried on L1, the chipping rate again of 1.023 million chips per second, and the code length of 1023 chips over the course of a millisecond before it repeats. But there are actually 32 different code sequences that could be used with the CA code. Remember that a very small portion of the code is dedicated to each one of the satellites. The precise code, or the P code, on L1 and L2 has, of course, a chipping rate that's 10 times faster than the CA code, 10.23 million bits per second, or million chips per second. The P code has the code length of about a week, and approximately 6 trillion chips. And when it's encrypted, it's known as the Y code. Here we have some power spectral density diagrams. They're a convenient way to illustrate signals, such as GPS signals and the signals of other constellations. They're basically a power per bandwidth sort of diagram. You can also say it as watts per hertz as a function of frequency. The actual definition of PSD is a Fourier transform of the autocorrelation function. But these are shown here to give you an idea of the power of the signal relative to its bandwidth. The power is represented on the perpendicular axis in decibels relative to 1 hertz per watt, or dBW. Now, this decibel watt perhaps needs a little bit of explanation. It was mentioned in Chapter 4. The decibel unit was really begun in the Bell Labs as a way to express power loss on telephone lines, logarithmically. In other words, a change of 1 decibel, an increase of 1 decibel, would be an increase of 27% in power, a decrease of 1 decibel, decrease of 27%. If there was a change of 3 decibels, that would be an increase or decrease of 100%. So, a decibel watt indicates the actual power of a signal compared to the reference of 1 watt. For example, the signal from a GPS satellite is about plus 13.4 decibel watts, and that same signal as received is about a negative 163 decibel watts. Therefore, these graphics show the increase or decrease in decibels of power in watts with respect to the frequency in hertz. So, here are 2 diagrams. On the left you have the L1 structure, and on the right you have the L2 structure. This diagram allows you to see some of the things we've already discussed. For example, this is the CA code in the blue on the L1 carrier, which of course is centered at 1575.42 megahertz and then spread over a bandwidth that is a spread spectrum. It's about 10.23 megahertz on each side for a total of 20.46. Then in the red, you see the PY code is in quadrature, 90 degrees from the CA code. It has really one main lobe and then the two side bands, and then the blue CA code has many lobes. Here we have the L2 signal diagram, centered at 1227.6 megahertz. There is no civilian code. It is only the PY code, and this is the L2 frequency. Now, this well-known arrangement is in the process of being changed, but currently this is the structure of the L2 signal. Now, September of 2005, an important step was taken in the modernization of GPS. You can see here the addition in this PSD diagram of the M code in the green. Now, the upper part of this slide is L1 that we just looked at, with the CA code in the blue and the P code in the red. And then lower, those codes are still there, but there's an addition, and this is the M code, the military code that has been added to the Block 2R-M satellites. One of the significant improvements coming from the Block 2R-M satellites is the increased L-band power on both L1 and L2, virtue of the new antenna panel that I mentioned a little earlier. The Block 2R-M satellites will also broadcast the new signal, and among them the M code. This new M code is going to possibly in future replace the P code, and it will be carried on both L1 and L2, and it has an advantage that the Department of Defense can increase the power of the code to prevent jamming. There was consideration to raising the power of the Y code to accomplish the same end, but that was discarded when it was shown to interfere with the CA code. Now, there's an interesting aspect to the M code. It is on the same bands, the L1 and L2, but still it's possible, even though it's carried on the same band, to separate it from the other codes on the carrier. Notice the split spectrum aspect of the signal. The lobes of the M code, the emphasis of the power is not in the middle as it is with the CA code and the Y code. That's because the actual modulation of the M code is done differently. It's accomplished by what's known as the binary offset carrier modulation. Now remember that the modulation of the CA code and the Y code is done by binary phase shift key. But the BOC, the binary offset carrier modulation that is used in the M code, has its greater power density at the edges, as you can see in this power spectral diagram. It's at the nulls of the L1. Notice that the center of the M code lobes, the highest lobes, are close to the center of the nulls on the P code. The architecture simplifies implementation, and it mitigates the interference with the existing codes. In a way, the M code stays out of the way of the CA code and the P code. So there's better spectral separation between the M code and the older codes. The M code is tracked by direct acquisition. That means that, just like our discussion earlier, the receiver correlates the signal coming in from the satellites with a replica of the code that it generates in its own circuits. So to recap, the M code will be carried on L1 and L2, but because of the binary offset carrier modulation, it will not interfere with the older legacy codes, the CA code and the P code. And here you see it on L2. The new military code on L1 and L2, of course, will be useful to the military, but it might not be terribly exciting to the rest of us. However, notice that there's something else going on. On the upper portion of this diagram, you see the L2 carrier, of course, with only the P code, encrypted as the Y code. That's in the upper part. And then lower, yes, here is the same L2 with the P code, but the M code's included, and now there's a new civilian code. Now this one is called L2C. Before this, there was no civilian code on L2. There was only the CA code on L1. However, these new 2R-M satellites will be carrying the L2C, a civil code on L2. We've been using the L2 carrier since the beginning of GPS, of course, but now there will be two new codes broadcast on that carrier. The M code and the new civilian code L2C. Now it's important to note that L2C really isn't just a copy of the CA code. It's different in several ways. Now the initial idea was perhaps to just have another copy of the CA code on L2 instead of L1. But Colonel Lovero was asked if there was time for some improvement in the CA code, and the answer was yes. So the CA code, of course, has been somewhat susceptible to distortion and interference, and its cross-correlation properties have not been as good as they might have been. So the L2C is actually a different code than the CA. Still, it's a civilian accessible code, and it's carried on L2 instead of L1. One of the differences between the CA code and the L2C is the fact that the L2C is made up of two elements, the civil moderate and the civil long. Now the civil moderate carries data. It carries a new navigation message known as CNAV. And here in this slide we see the difference. On the left, you have the old navigation message in sort of a shorthand form. And on the right, you see some of the new aspects of the CNAV code. Now you notice that both 300 bits the old navigation message was broadcast at 50 bits per second. The CNAV is broadcast at 25 bits per second. Both have 300-bit subframes. But the CNAV is a bit more flexible and compact, and it allows a receiver to get a first fix on a satellite much faster than the older navigation message. Now, as I say here, the information in CNAV, almanac, ephemerides, time, satellite health, etc., is very similar to the original navigation message. But CNAV uses a 12-second, 300-bit message packet. One of every 4 of these packets includes clock data. 2 of every 4 contains ephemeris data, and so on. CNAV can accommodate the transmission of the information in support of 32 satellites, using 75% or less of its bandwidth, and a fraction of the available packet types. For example, this allows flexibility, such as having a differential correction right in the navigation message. We've talked earlier about how in DGPS, RTK, even in some wide area DGPS systems, there are broadcasts that can be accepted by the receiver that will allow it to correct its position in real time. It would be very useful to have such a correction available right in the navigation message, and CNAV presents this possibility. Also, there is a packet in CNAV assigned to the time offset between GPS and GNSS. So one of the things we'll talk about is that GLONASS's time standard is different than that of GPS, and the difference can be loaded into the navigation message. So there's some preparation here for the GNSS future. Also, each packet contains a flag that can be turned on and off very quickly to indicate that a satellite is unhealthy. This is quite useful for safety of life, things such as ambulances and so on. Because if a satellite should not be used in positioning, if it will corrupt the results, it's important to know that immediately in real time. It's great to have a system that can provide that. CNAV also has enough room to accommodate up to 63 satellites. You see the number 63 on the bottom of the right-hand column in green. This, again, is looking forward to these larger constellations that may be used in GNSS. There's also the interesting concept of forward error correction in the CM or civil moderate code. This is all on L2C. An illustration is to imagine that every individual piece of data comes to the receiver twice. Now, if the receiver has the knowledge of what the protocol, the format of this data should be, and it has two versions of it, then it should be able to compare each of those two to the protocol. If they both match, no problem. If one matches and one doesn't, then the one that matches is accepted and the other rejected. If neither one of them match the protocol of the data, they're both rejected. So this allows a receiver to correct its signals on the fly. It can correct, eliminate those that are wrong and accept those that are right. In this slide, I try to answer the question how it's possible on L2C to have two codes, the CM code and the CL code, simultaneously operating on the same signal. Well, it's known as multiplexing, and we discussed that briefly when we were talking about receivers. Except in this case, it's chip-by-chip time multiplexing. The CM code, the moderate length code, goes through 10,238 chips before it repeats. It repeats every 20 milliseconds. But the CL code, the long code, repeats after 1.5 seconds. Those lengths give you very good cross-correlation protection. In fact, both are longer than the CA code and present a subsequent improvement in autocorrelation. This is because the longer the code, the easier it is to keep the desired signal separate from the background. In practice, this means that these signals can be acquired with more certainty by a receiver which can maintain lock on them more surely in marginal situations where the sky is obstructed. So, it is possible to have these two signals, the CM and the CL, on the L2C because the receiver can shift back and forth between the two with good, solid cross-correlation and lock on to the signals even in circumstances where the sky is obstructed, better than one can with the CA code. it's important to note that the L2C is actually slightly weaker, 2.3 decibels weaker than the CA code. And it's surprising that this is not a disadvantage, because the receiver can track the long dataless CL, that's the long code on L2C, with a phase-locked loop instead of squaring Costas loop. In other words, the long dataless sequence of the CL provides for correlation that is actually about 250 times stronger than the CA code. So despite the fact that its transmission power is 2.3 decibels weaker compared to the CA code, the L2C has 2.7 decibels greater data recovery and 0.7 decibels greater carrier tracking. It's actually more solid even though the power is slightly less. Okay, here I ask, well, what does that mean? What does that mean in English? Well, like the fellow looking up here into what is probably an obstructed sky with his GPS receiver, it means that with L2C there will be a better tolerance for interference, increased stability, and GPS will work better in obstructed areas near buildings and urban canyons. Fewer cycle slips. Another really good, solid, practical advantage is that this is a civilian code on a separate frequency. Now, as you may remember, one of the ways that you can model the ionosphere with a dual frequency receiver in carrier phase is that you have two signals that are actually at different frequencies. And since the ionosphere is dispersive, that means that one can model the total electron count to some degree and take out a good deal, although not all, of the ionospheric delay. However, those that have been operating purely in code phase or pseudo-range positions have not had that advantage to be able to model the ionosphere. However, now, with L2C on L2 and CA code on L1, there will be two civilian-accessible codes that can be received by a code phase pseudo-range receiver, and theoretically it would be possible to model the ionosphere with code. This should improve the positions available from purely code phase receivers quite a bit. So even if carrier phase ultimately is the key that delivers the high accuracy that we depend on, it's always been the codes that get us in the game. They are the front end that allows the receiver to lock on to the satellites. And our receivers have been combining pseudo-range and carrier phase observables in innovative ways for some time. But those techniques can be improved because while the current methods work, the results can be noisy and not quite as stable as they might be over long baselines. It will be cleaner to get the signal directly once there are two civilian codes, one on each carrier. And it may actually make the chipsets inside our receivers a little simpler, and it could lead to a little bit of a reduction in the cost of such receivers as well. It's worthwhile to recall that the L2C has an overall chip rate of 1.023 MHz, just like the CA code on L1. And such a slow rate can seem to be a drawback. However, it's important to know that the lower the chip rate, the slower the rate of the drain on the battery. So it's possible that the slow chip rate can not only reduce the size of the chipset, but also increase the life of the batteries driving the receiver. L2C is going to be very good for the consumer market. The first Block 2RM that carries the L2C and the M code was launched September 2005. But it'll be some time before the constellation of the 2RMs are at operational level. Additionally, aviation authorities do not support L2C. It is not in an aeronautical radio navigation service protected band. It happens that L2 itself actually occupies a band that includes ground-based radars. There's a little bit of a difference in that aspect with L5. This is the new carrier that everybody's talking about. Now, as you know, we've had L1 and L2, but a new carrier is coming, known as L5. It will be centered at 1176.42 megahertz, which is 115 times the fundamental clock rate. The basic structure of the signal looks very much like L1. There are two codes. They're modulated using quadra-phase shift key. However, the I, or in-phase signal, carries a data message, and the other is dataless. This is very similar to what we just discussed with L2C. Both have equal power. The data that is carried on L5 is compact, flexible message, similar to that carried on L2C CM. L5 will also utilize the same kind of time multiplexing in broadcasting its two codes as does the L2C. However, unlike L2C, L5 will have the benefit of its place in a band designated by the ITU for Aeronautical Radio Navigation Services, ARNS. Therefore, it will not be prone to interference with ground-based navigation aids and will be available for aviation applications. This is a very good thing. It's also quite helpful that no other GPS signal occupies this band. However, L5 will share space with one of the signals, that's his E5A, from an entirely separate satellite system, Galileo. This is the European contribution to GNSS. This overlap, this sharing of this frequency is actually a very good thing, and we will be talking about that shortly. L5 will have one signal modulated with data and one without. Now, L5 doesn't carry military signals. It achieves the power split by using two long equal-length codes in phase quadrature on each satellite, just like we see in the diagram, phase quadrature. Both have 10.23 megahertz chipping rate, the same as the fundamental clock rate. This is the same rate that's been available on the P code from the beginning of the system. However, remember, this is not the rate that's been available to civilian users. So this is the fastest chipping rate that will be available to civilians. It'll have the same overall length as CM on L2C, but L5 will have the only civilian codes that are both 10 times longer and 10 times faster than the CA code. So the risk of interference is very low, and good news, the dataless signal will be much easier to acquire under unfavorable signal-to-noise ratio conditions. And put directly, the fast chipping rate is really good news because, remember the rule of thumb we talked about in the first lesson. The maximum resolution available in a pseudo-range is about 1% of the chipping rate of the code used. The faster the chipping rate, the better the resolution. It also improves multipath protection. L5 will also have higher power than L1, almost 4 times more. And the increased power is good news because, as you know, the GPS signals as they stand currently are quite weak. L5 will have a wide bandwidth, about 20 megahertz, and will also use this forward error correction that we talked about. Here is the satellite on which the L5 will be introduced, the Block 2Fs. F is for follow-on. These satellites have a very long lifetime, 12 to 15 years. They're quite an upgrade. They have faster processors, more available memory. They carry 2 rubidium frequency standards, or clocks, and 1 cesium. The onboard navigation units support the new navigation message, and like 2R, they can be reprogrammed in orbit. However, it's going to take some time before the 2Fs really are operational. The dozen or so 2Rs that need to be launched will have to reach the end of their functional life before the 2Fs are launched in earnest. So it will be some time before L5 will be available operationally. The first 6 Block 2F satellites are expected to have a mean mission duration of about 9.9 years. But the 2Fs will have all the codes we've discussed. They'll have the L2C on L2, they'll have the new broadcast L5 carrier, and of course, as we've discussed, the L5 will not cause interference to existing systems. Okay, so here we are. In the top of this slide, we see L1 and L2 as they currently exist. In the next tier, we see the L1 with the addition of the M code, and substantially the same otherwise. But the changes in L2 are both the M code and the new L2C civilian code. Then, with the 2Fs, the third 2Fs, we'll see those changes and the addition of L5. The new signals tend to have longer codes, faster chipping rates, and more power than the existing codes. In practical terms, these developments lead to faster first acquisition or faster initialization, better separation between codes, reduced multipath, and better cross-correlation properties. Now, here is a chart that provides somewhat similar information. However, you can see that what this indicates is that the 2Rs, as they stand right now, and then the 2RMs will have the addition of the M code and the L2C, and then the 2Fs will have all of the codes that we've discussed, including L5. As far as when initial operational capability will exist for L5, I say here 2010 and 2020, somewhere between those two. Of course, no one can say for sure when it will occur. Full operational capability will follow within 5 to 10 years after initial operational capability. It's impossible, of course, to predict with accuracy. Aviation is looking forward to L5, of course, because it's promised for precision approach capability, which will be very useful in aircraft. Of course, as we wait for full operational capability on these new signals, there will be opportunities to track them when they are not yet fully operational. Considering one of our largest error sources, as you know, it is ionospheric delay, it's inversely proportional to frequency of the signal squared. So L2's atmospheric bias, the ionospheric delay in L2, is about 65% larger than L1, and it follows that the bias for L5 is the worst of the three at 79% larger than L1. And so, of course, L1 exhibits the least delay because it has the highest frequency of the three carriers. When a receiver is in an environment where some signals are quite strong and others are quite weak, the strong signal from one satellite can cross-correlate with the codes a receiver uses to track the others. In other words, the strong signal can actually block the collection of the weak signals. To avoid this, a receiver is forced to test every single signal to avoid incorrectly tracking the strong signal it doesn't want instead of the weak signal that it does. In this respect, the signal that is going to have the best cross-correlation protection is going to be L5. There is one more GPS signal on the horizon that we should mention. L1C. As a result of an agreement reached between the US and the EU, there's another signal, another civilian signal that is in the beginning stages of development. Part of that deal involved the interoperability between GPS and Galileo for a signal on L1. This signal known as L1C. And will be only one of two common interoperable signals shared by both. This will be very useful. In other words, it will be a new signal on the L1 carrier that will be interoperable for Galileo and for GPS. It also appears that it will be interoperable with QZSS, the Japanese quasi-zenith satellite system. Now, interoperability means that it will be possible for receivers to receive the signal from satellites that will be Galileo satellites and satellites that will be GPS satellites, meaning that you will have an increased constellation from which to collect the signal with your receiver. These developments open up extraordinary possibilities of improved accuracy when one considers that there may be eventually a combined constellation of 50 or more satellites all broadcasting this same civilian signal. And all of this is made possible by the fact that each of these different satellite systems utilize carrier frequencies centered around what we call L1, 1575.42 megahertz. Now, the details of the design of this particular signal are still in flux. However, as you see here, the MBOC modulation of the L1C means multiplexed binary offset carrier. The thing to notice is that these, again, the two lobes on each side of the center frequency, so that there is not interference. Know that the Galileo constellation, this is the European Union constellation of navigation satellites, will be able to broadcast on 1575.42 megahertz, just as we do with our L1, and will be able to carry this signal. That will mean an increase, dramatic increase, in the number of satellites available The data portion of L1C will carry a navigation message, and this will allow receivers to reach their first fix or their initialization fast. It will also have the forward error correction that we've talked about. The reason perhaps that there are so many signals now crowding onto L1 is, remember, L1 is the carrier that has the least amount of ionospheric delay of the carrier frequencies we've discussed. There's the CA code, the PY code, the M code, and perhaps the L1C code.